Chapter 8. In Chapter 8, we look at making cost estimates and why we do cost estimates. Well, this is the relationship between our cost object and our cost drivers for the purpose of predicting costs. This is important for overhead management, for using estimated costs to create budgets, using estimated costs to allocate overhead. It helps us with all of our planning, decision making, and control. So we start with cost estimates and we use those to create budgets. That's part of planning. We also use them for decision making. And then for control is when we come back and say, how close did our actuals come to our estimates? That's part of control. We have 6 steps in our estimate process. One, first we define the cost object. What are we collecting costs for? Then, what are our cost drivers? What is the what has a causal factor with that cost? What has a relationship with that cost that drives that cost? We also want consistent and accurate data. So consistent means that we record it or we calculate it on the same accounting basis. And accuracy is the reliability of the data. Then we graph the data. We want to look for any unusual patterns, non-linear, and outlier observations. So things that are outside of our normal cost behavior patterns. Remember, most cost behavior patterns are linear to some way, and we want to see when we graph them what kind of outliers or nonlinear information we have. Then we have a cost estimation method. We have the high-low method and the linear regression method. Then we want to assess the accuracy of that cost estimate. So one measure is the accuracy of the estimation method is the mean absolute percentage error, also called MAPE, or regression analysis. That's generally regarded as more accurate than the high-low method. So we're going to look at this example. We want to estimate what our future maintenance costs are for a large manufacturing company. We have information about our costs from January through July and the usage. So we've graphed that information. We're going to estimate first using the high-low method. So our accountant feels there is an economic relationship between the maintenance cost and monthly operating hours. That's our cost driver. So we've collected what are our total maintenance costs and what are our total operating hours. So if you remember, the high-low method looks at the change in cost divided by the change in the cost driver, using a high measure and a low measure. When we graph this information, we're looking for linear data. So we would want something to be linear in order for it to really show that it was a good cost driver for that information. Then when using the high-low method, we use the equation for a line, linear algebra. So our line is y, the total estimated cost. A is the intercept, or the fixed cost, plus b times x. B is the slope of the line, which is the unit variable cost, and x is our cost driver. In this case, the number of operating hours. So using the graph of operating hours, we pick 2 data points, usually the highest and the lowest point in the data set. So we're going to look at February, the low point, and April, the high point. So we take the change in hours and the change in cost. We divide the change in cost by the change in hours, and we come up with a variable cost of $1.80 an hour. We then put that information in to the equation using the total cost amount we have to calculate what that fixed cost amount is. This gives us our cost equation, which is total cost equals fixed cost of $16,525 plus our variable cost of $1.80 times our cost driver, which is operating hours. So this is operating hours within our relevant range. Our relevant range is approximately 3,325 hours to 3,615 hours. We can use this equation to estimate our monthly maintenance costs. So we're going to estimate that for the month of August, if we anticipate 3,600 hours being used, that we would have $23,005 in maintenance costs using the cost equation we just calculated. The pros of the high-low method are that it looks at a graph to identify any outliers and nonlinear information. The cons are that it relies on only 2 points, and the selection of those 2 points requires judgment. We discard most of the data available. Our other method is regression analysis. Regression analysis is a statistical method that gives us a cost equation by looking at a set of data points and the sum of the squares of the estimation errors. So our errors are squared. This method is also sometimes called least squares linear regression. So with the regression analysis, or the linear regression analysis, we use Excel to perform the regression analysis. We have a dependent variable, which is our cost to be estimated. The independent variable or variables are a cost driver used to estimate the cost. When one cost driver is used, the regression model is referred to as a simple regression model. When we have 2 or more cost drivers, then the regression model is referred to as a multiple regression model. A simple linear regression has only one independent variable. The model equation is as follows. So y is the amount of the dependent variable, or total cost to be estimated. A is our fixed quantity, also called our intercept or constant term. X is the value for the independent variable, or the cost driver for the cost to be estimated. And then B is the unit variable cost. This is our coefficient of our independent variable. And then E is E is our estimation error, for which the data point is the distance between the regression line and our data point. So we have some information here. We have 3 months of data on supplies, expenses, and production levels. Normally, we would have more data points involved in regression analysis, but in this example, we just have the 3 months of information. We draw a line with those graphed points. Then we would do a regression analysis. So our regression estimation line is obtained from a computer software application, usually Excel. So we'll do an Excel example in class. So the regression solution we receive from Excel is that A equals 220 and B is 75 cents. So we can use that equation for our estimated cost. So when we have 125 units in month 4, we would put that into our equation, y equals 220 plus 75 cents times the number of units. The pros of regression analysis is that it's statistically precise. It helps us estimate future costs. It provides quantitative measures of its accuracy and reliability. It gives us the statistical validity of the regression. The cons are that it can be influenced strongly by outlier data points resulting in a line that is not representative of all of the data. So when we're looking at the reliability and the precision of our regression analysis, we're looking at actual relationships among the variables as measured by R squared, which is our the coefficient determination, the t-value, and the p-value, and our standard error of the estimate. So we're going to look at a readout from a regression analysis. R squared is the number between 0 and 1 that describes the explanatory power of the regression, so the degree to which the change in y can be explained by changes in x. So this shows us how good a fit our cost driver is for that information. The maximum value for R squared is 1, or 100%. The t-value is a measure of the statistical reliability of each independent variable in the cost function. In a multiple regression model, low t-values signal the possibility that 2 or more independent variables may be highly correlated with each other, and we might want to remove one of those variables. If we have a low t-value, we should look at them, evaluate them, and possibly remove them. We might not have selected the best relationship in our cost equation. P-values looks at the risk that the true value of a given cost coefficient is 0. So low p-values imply rejection of the assumption of a relationship between the dependent and independent variables. Normally, p-values of 5% or less are expected in our usable regression models. And then we have our standard error of estimate, which is a measure of the precision and accuracy of a regression's estimate. We want to establish our confidence intervals for cost estimation. So when we look at that, we want a confidence range of 67%, or our unknown true value of the estimate, should fall within this range of the amount predicted by the regression equation. A regression with high precision will have an SE value that is relatively small compared to the average value of the dependent variable. When we look at this regression output, we are given some information here. So the SE, 221.7, that's our fixed cost. Then we have t-value and p-value and our R squared amount. The R squared is less than 0.5. This is lower than desired. However, the SE is approximately 1% of the mean of the dependent variable, which is good. The t-value on the estimated coefficient is slightly more than 2, which implies a low probability that there is no relationship between monthly maintenance costs and changes in units of output. So why is the R squared relatively low? So we look at the month of May. In May, our maintenance costs are unusually low compared to the other months. So we want to use a dummy variable to potentially capture seasonal effects. So we've assigned a value of 1 for May and a value of 0 for the other months. After this addition to our model, then the quantitative measures all improve. So apparently this seasonal fluctuation was distorting our results. So if you go back and we look at the graph that was prepared, we see this nonlinear information here where May doesn't fit our line. April also doesn't fit our line. So these outliers can influence how that regression analysis comes out.